Hi all. This video we see a paper titled Latent Neural PDE Solver for Time Dependent Systems from Connie Mellon University. And mostly the objective of this paper is to build a circuit model for accelerating the numerical simulations involving high fidelity PDEs. So they have two stages. One is projecting the high dimensional fidelity data into a low dimensional space using a nonlinear projections operator called autoencoder, and once that is projected it is temporarily evolved in a reduced space using a conventional neural network like convolutional neural networks. So they claim that it significantly reduces the computational cost and they benchmark against 2D 3D fluid force and claim that it has a competitive performance compared to the other models. So now the motivation here is the time-dependent PDE modeling physical processes requires very fine discretizations and high-fidelity data, where that has it takes a lot of time to reach the convergence. So in that occasions, they involve surrogate models involving deep neural network to improve the efficiency of the simulations. So here, for since it is involving a time-dependent data, it maps the state from the current state to the future state, and the author here makes a two-stage preparation for building a surrogate model. One is to project a high-fidelity, high-dimensional data into a low-dimensional space using a deep autoencoder, like projecting a 64 cross 64 grid data into a 8 cross 8 grid data. So this once the data are projected into a low dimensional space and that it is temporarily evolved in this low dimensional space, and those evolutions being trained using a standard neural network like convolutional neural network algorithm. And the proposed framework, like I said earlier, they tested on 2D and 3D time dependent PDEs. So related work there are that neural-based PDE solver building a surrogate model is classified or categorized into three groups. First is purely data-driven model, which have training data, and we try to build an input-output model using only a standardized neural network architecture. The second one is we embed some physics inside the loss functions instead of having a training data. Those loss functions would guide and guide during the training stage. And the third one is embedding the physics-based operators involved in PD into building a neural network architecture like neural ODEs. So one among that is here we are trying, the authors utilize this Fourier neural operator based architectures, and it benchmark against this one with this two-stage surrogate model. So the two-stage involve, as mentioned earlier, it's first build an encoder-decoder model based on convolutional neural networks. We try to minimize the computational complexity for evolving the dynamics. Once that reduced dimensional space is being built using the nonlinear projections, we can improvise a standard recurrent neural network like LSTM, but here the author prefers to go for convolutional operators to learn the dynamics of the time-dependent system within this latent space. So this diagrammatic is beautifully representing what we have discussed so far. The first stage, they build an encoder-decoder model. This is the full high fidelity data, the PDE state, and the encoder tried to project it into a low dimensional space, the unknown latent space represented by ZT. And once we this train the encoder and decoder is trained enough to produce exactly the input and output, error is minimized. This embedded is confident enough to build a low dimensional dynamical systems, and that low dimensional dynamical system is built by using a propagator called a conventional neural network operator, and try to make the input as a ZT, and the future output would be a ZT plus 1 is got back, and that would be fed again into the decoder to get the original output. So these are the simplest methodology, and they tested against two problems. One is a two-dimensional problem, and which and since it's a Markovian model, the temporal dynamics only involved on the present state to compute the future state, and it's a discretized domain. And the reason for them to build instead of going for a post discretization kind of multi-grid, the reason is they may be losing the information which is related kind of Nyquist frequency called a Fourier discrete Fourier operator. So they build an auto decoder nonlinear things, so that they claim that that would preserve the preserve and keep the accuracy as far as good as possible. And it's also been proven in many other outside applications like compressing the image data. And these are some of the mathematics behind those encoder decoder information, which is not that needed for our descriptions. And the experiments involve the two time dependent fluid flow problems. One is 2D and 3D, and that is the built model is benchmarked against the neural ODE called the Fourier neural operator approximated by FNO, and the grid resolution is 64 and this is a 2D compressible flow based on vorticity equations. And the time is evolved from t equal to 5 to t35 for 30 seconds, and they have to build a high fidelity data. They use a pseudo spectrum model, and they have 1,000 different kind of trajectories that they build based upon the initial conditions and the force functions. And based on that, 900 is used for training and 100 is used for testing. And similarly, a 3D smoke buoyancy equations are modeled by Navier-Stokes equation and additional advection equations. And they also here they build 1,000 trajectories, and some of the trajectories are used 2,200 trajectories, sorry, and 2,000 trajectories are used for training and 200 for testings, which is too high for putting into a training set. Then they build an auto encoder and decoder model is based on again convolutional layers, and these are some of the details how they build up, and which is not directly related to our objective of presenting this paper. And the propagator is again involved a convolution operator to propagate from CT to CT plus 1, as I mentioned earlier. The benchmark baseline surrogate model they have taken here is called FNO, Fourier neural operator. And the training involve 150k epochs, and the learning rate is fixed in 3 minus 5, and they have used a batch size of 64 cross 16 respectively for 2D and 3D, and the FNO also trained with the same learning rate 5e minus 4, and they use same 150k operations. And the result they claimed is it's compared to the FNO and other models they benchmark again. This model seems to be a promising one because the temporal thing is happening in a low dimensional space, and it is 4 times closer than the fine resolutions. So these are some of the results, and it is related same like what they claim is it has a better performance. And there can be various ways of training this. One is first training the encoder and decoder first, then they can train the temporal dynamics separately. It's called a two-stage, and can be other possibility to train all the things in a single stage itself. But they claim that the two-stage gives so much better performance compared to the single stage, like putting the temporal dynamics training and also the projection training at a single phase. So what author claim here, they build a purely data-driven framework for predicting the time-dependent PDEs, and the temporal model is been evolved in a much reduced space, and the latent space is similar that these applications of evolving in a reduced space is similar to of a generative model in a pixel space. And the future direction would be to not to go for standardized visualizations, and they will be going for arbitrary measures and complex geometries. So the author is here, what they try to claim here is nonlinear projections and evolving the dynamics in the reduced space. These are the main objective of this paper, and they claim that this operations building a surrogate model seems to be a very good promising for the future directions. And and the future they might be giving a paper to give a better results on a very realistic problems involved in a complex geometries and complex mesh architecture. Thank you.